This is the first part of my two-part videos about linearizations and differentials. In this video, we're going to focus on differentials. So I'm going to start by defining the differential dy. So dy is our differential. It is equal to the derivative times dx. I'm going to show you what these quantities mean through a picture. So I have graphed a function, that is this curve right here. And then I've also graphed its tangent line, the straight line I have shown in blue. So I have a function and its tangent line. At the point of tangency, the function and the tangent line are equal. They share that point. If I move over in the x direction, we're going to call that delta x, a change in x, and that's going to be equivalent to our differential dx. So dx represents a change in x, or you could think of it as a run. You're moving over. Then the change in y along that graph of the function is delta y. So if I move over in the x direction, my y values are changing as well. My differential, the dy, is actually the change in y along the tangent line. So one thing to notice here is that if you are close to that point of tangency, if your delta x is small, if you don't go over very far, the dy and the delta y are really close together. So the tangent line and the function are very close together when we are close to that point of tangency. So let's take a look at a couple of examples. We'll start by just computing the differential. So compute the differential dy for the function f of x equals x cubed minus 2x plus 3. The derivative of that function would be 3x squared minus 2. Our differential dy is simply that derivative times dx. So dy is the quantity 3x squared minus 2 times dx. And that's it. There's my differential. All right, let's modify this problem a little bit. We'll compute our differential, but let's compute our differential when x is 2 and dx is 0.1. And then I actually want to compare that differential dy with delta y to get a sense of what this differential is telling us. So we just computed our differential dy is our derivative times dx. We can plug numbers into this. We can compute the differential when x is 2 and dx, our change in x, is 0.1. So I just plug those numbers in. 3 times 2 squared minus 2, that would be 10, and then times 0.1 is 1. So my differential in this case is 1. And what this number is telling me is that if I start at x equal 2 and I go over 0.1 units, my y values along the tangent line should go up 1 unit. Now the interesting question is, how does this compare to delta y? How does this change in y along the tangent line compare to the change in y along the graph of the actual function? Well, to compute delta y, I'm just going to compute what is f of 2. So I took 2 and I plugged that into my function, 2 cubed minus 2 times 2 plus 3, and I got 7. Then, if we go over 0.1 units, if our dx, which is the same as our delta x, is equal to 0.1, we're now at an x value of 2.1. So I'm going to take 2.1, I'm going to plug that into my function, and I ended up getting 8.061. So the delta y is going to describe how these y values are changing. And if I take 8.061 minus 7, I get 1.061. And the thing to notice here is that the dy and the delta y are really close together. They're almost the same value. And that's something we can expect to happen anytime our dx is really small. We're basically saying that our tangent line is a great approximation for this function when we're really close to that point of tangency. Let's take a look at an application problem. So here's one application of differentials. The edge of a cube was found to be 20 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error in computing the volume of this cube. So I have a cube. So there's my cube. I'm going to call the sides of this cube x. And the lengths of the sides, the x, is 20 centimeters. And my dx, the change in x, is what we're going to call that error in measurement. So our x values might be off by 0.1 centimeters. That's going to be our dx. In this problem, they are asking us to find dv. They're asking us to find an error or a change in the computation of the volume. So volume of this cube would just be x cubed. And so I can compute that differential, dv, by taking my derivative times dx. And the derivative of x cubed is 3x squared. So dv is 3x squared dx. Now I'm going to plug my numbers in. I know that x is 20 and dx is 0.1. So 3 times 20 squared times 0.1, that's 120 centimeters cubed. So this is telling me if I change the measurement of a side of this cube by 0.1 centimeters, I can expect my volume computation to change by 120 centimeters cubed. Now, is this a big change or a small change in volume? It often is more useful to express this as a relative error or a percent error. So your relative error is going to be that change in volume divided by the total volume. So our error in our volume computation is 120 centimeters cubed, but if x is 20, the actual volume would be 20 cubed. And if I take 120 divided by 20 cubed, I got 0.015, which written as a percentage would be 1.5%. So with this possible error, I can expect that I might get a 1.5% error in my volume computation. I'm going to continue this topic in my next video, which is going to cover linearizations or tangent lines in more detail.